Hi, everyone. Let's wrap up the alkene reactions. So we have a few more to go. And these are more minor reactions, but they're still important. Or in other words, yeah, they can show up on the exam. So we're in Key Concepts, Unit 2, Part 6. The first page of Part 6 looks like this, hydrolysis of epoxide. So scroll down so you find where we left off. And we need to cover this part now. This is the oxidation of alkene. So oxidation reaction are back again. You may remember those. Hopefully you remember those from general chemistry. And what you need to remember at this point is that oxidation is loss of electrons. Reduction is gain of electrons. Those acronyms were oil rig, oil. Oxidation is loss, rig, reduction is gain of electrons. Okay, that's cool. And now that we remember that, we're just gonna put it aside. So we got other patterns that we'll remember. They'll help us predict the products. Okay, so there's lots of ways to oxidize. In organic chemistry, oftentimes, not always, but often, oxidation means adding oxygen to a molecule. And that's the pattern we're going to see here. So let's start the first way to oxidize an alkene, and that's through ozonolysis. So let's get an alkene, maybe this one here. What is this? This is 2-methyl propene. Yeah, isobutylene is a common name. And let's cut it with ozone. Let's perform ozonolysis. We saw the word hydrolysis before. Hydro, referring to water. Lysis, meaning to cut. Yeah, so we cut with water, cut one molecule into 2 pieces through a hydrolysis reaction. Now we're going to use ozonolysis to what? Cut a molecule into 2 pieces using ozone. Yeah, so we're not actually going to get up in a jet airplane and go up to the ozone layer. No, we'll manufacture some ozone here at the ground level of planet Earth. Ozone's O3. And then the first reaction, that's what the 1 here stands for. Mix your alkene with this ozone gas, probably in a solvent, bubble it, the ozone through there, let it react. And then after that reaction is done, in a second step, you add zinc and an acid. So oftentimes we'll just write H3O plus as our acid, some source of H plus hydronium ion. If you look at some homework problems, sometimes they specify the acid. Doesn't matter. The key is ozone, O3. And there's no other reaction that has 3 oxygens, 1 oxygen. Sorry, I'm not saying that right. Oxygen with 3 atoms, 3 ozone, O3. 3 oxygen atoms linked together. It's going to do the cutting reaction. So what I tell students is kind of get a little graphic here and say, okay, I was taught that this was a cleavage reaction, which is where you take, I've got my hand here, I'm going to do a karate chop. You can actually take a butcher's cleaving knife, this big knife, I should have got a picture of it, that's useful for chopping meat into pieces. So think of ozone as a big sharp knife, and you're just gonna give this double bond a karate chop. Hi-ya! And we're gonna just cut it right down the middle. So my little zigzag line, just cut the alkene into pieces. Okay, so what are those 2 pieces? Well, if I had better control of my computer screen, I could actually just cut and paste this, but I'm not going to do that. So the left piece, so the left side of the zigzag line has 3 carbons and a piece of the double bond. And then the other piece is just this remaining fragment, just a little sliver of a double bond. What is this representing? This molecule is so small that the skeletal drawing is a little confusing. So let's expand it. Let's redraw the molecule where we see all the C's and H's. I want to do it again. Okay. 2-methylpropene. Give it a karate chop. Hi-ya! Right down the middle. Chop. Okay. So then let's put it up here. Where are we going to put this? Draw it this way. We got the left fragment. There's a methyl group up high. There's a carbon and another methyl group and a little stub of a double bond. On the other side, there's a CH2 and a little stub of a double bond. Okay, what's going on here? So you see how the skeletal drawing, it's the same as this expanded condensed drawing, whatever it is. So going back to the karate chop analogy, your butcher's cleaving knife. So you cut this piece of meat, this alkene, into 2 pieces, and maybe it bleeds a little bit. So take 2 cotton balls and stop the bleeding. So cotton ball number 1, cotton ball number 2. Yeah, those are oxygen atoms. And here are the products. So when you have an alkene and use ozone, and you must follow it after you mix the ozone in. Afterwards, you add zinc and acid. Cut the double bond into 2 pieces. And where the double bond gets cut, each end gets capped with an oxygen. And you can draw it like this. That does look a little funny. So maybe you would actually expand it to make it clear what the structure of the molecule is. It's your choice. Oh, so down here I need to put my cotton balls on. There we go. And what does it make? Well, what's the name of this functional group? We got carbon double bond O with 2 carbons attached to this carbon. That's a ketone. Cool. What's this one with C double bond O, but there's a C with an H. That's an aldehyde. And specifically, the aldehyde that does not have any extra carbons, only 1 carbon, this is formaldehyde. So in the bio department, they use this for preserving specimens. Yeah, so you make a ketone and aldehyde. Now, you don't always do that. You don't always get ketones and aldehydes at every oxidation reaction with ozone. Let's try a different molecule. Let's try trans 2-butene. Give it a karate chop with ozone and zinc and dilute acid. So hi-ya, chop it into 2 pieces, right across the double bond. Yep, got it. Put the little cotton balls, stop the bleeding. So there's my left fragment. And then here's my right fragment. Hey, these are exactly the same molecule. So why write the same thing twice? You only have to write it 1 time. Again, the organic chemist really doesn't pay attention to balancing reactions when they write out their equations. So you don't have to write both of these unless you want to. Okay, so in this case, you don't get any ketones. We just get a pair of aldehydes. And if you take other molecules, maybe you just get a pair of ketones. There you go, that's mild oxidation. Cool. I'm calling it mild oxidation because it's pretty straightforward. Cut the double bond into 2 pieces, cap them with oxygens, that will become a ketone or an aldehyde. You can use another oxidizing agent, something other than ozone. And the one we will have for this class is permanganate. Now, it turns out permanganate is a stronger oxidizing agent than ozone, and it attacks the products. So the pattern's kind of the same. So right down here under key concepts, we got the reagents, which consist of potassium permanganate, KMnO4. And if you go to other organic textbooks or websites on organic chemistry, you'll see different reaction conditions. Sometimes they're neutral, sometimes they're basic. Change the products. We're just going to stick with dilute. That's a key. It's dilute acid. So let's use the same 2 alkenes. We just saw ozanolysis. But this time we're going to treat it with KMnO4. Wow, what's up with my handwriting? That's a little better. Okay, and on exams, I might get sloppy and just put KMnO4, so you can too. If you have to supply reagents on my exams, potassium permanganate is fine. If I'm a little more careful, I might throw hydronium ion under the arrow. I should. Okay, so what happens? Well, the pattern begins just like ozonolysis with a karate chop. Chop them in half. And then let me put the products in parentheses because these are actually intermediates. So what are our two products for ozonolysis? Well, you got the left side with a little stub. You got the right side with a little stub. And then use your little cotton balls to make your two products. Okay. And then it turns out KMNO4 attacks aldehydes. It leaves ketones alone. Although if you look in other organic textbooks, you can actually get a reaction that occurs. We're not gonna look at that one. So it turns out aldehydes react yet again. And so check your products. Do I have any aldehydes? Oh boy. Functional groups. I know that was a unit 1 concept. Well, it comes back here in unit 2. This first product is a ketone. That's done. The permanganate doesn't react with that. So that is one of the products. When this alkene reacts with the KMNO4, you do make this ketone. But the aldehyde reacts again. If it's formaldehyde, or more importantly, if that carbon has 2 H's, the whole molecule turns into carbon dioxide. I'll give you the reason in a minute. It's not on the exam. But that's what happens. Formaldehyde, the aldehyde with linked to 2 hydrogens, gets oxidized again by permanganate ions, and turns into carbon dioxide. And those are our final products. Do you always get carbon dioxide? No. Down here in the bottom reaction, let's try this. Karate chop, yeah. We're going to get the same molecule 2 times. Is this an aldehyde or a ketone? I know some of you are saying, wait, where's the other piece? Okay, you draw it in there. But that's the same thing. You don't have to draw it twice. Is this an aldehyde or a ketone or something else? It's an aldehyde. Darn it, that's not the final product. So put that in parentheses. This carbon, this aldehyde rather, the aldehyde carbon only has 1 H. So it's not formaldehyde. So change the H to an OH. Change it to an OH. Good. You make an alcohol, right? No, that's not an alcohol. This is a carboxylic acid, right? Okay, so that's what you have to do. I know I don't like permanganate as much as I like ozonolysis. Ozonolysis, O3, straightforward, chop in half, cap with O, you're done. Permanganate does the same pattern initially, but then if there are any aldehydes, they get oxidized again. I promise a little explanation of that. So here you go. Let me just cap this by saying it's not on exams. But for some of you, I know you like having reasons and understanding the reason why something happens. That sometimes solidifies in your head. It does for me. If I have a reason, I'm more willing, or not, maybe my brain's more willing to accept it and remember it. Okay, so here's the idea. If we had just any other aldehyde, a normal one where the carbon is attached to only 1 C. I'm not going to show a mechanism, but essentially what happens is that the hydrogen is removed and replaced with a oxygen that also has a hydrogen. It's like an alcohol group, but now those molecules are carboxylic acid. Same pattern with formaldehyde, but there's 2 H's. And so potassium permanganate swaps out both hydrogens for alcohol groups, but it's not an alcohol now. It's a carboxylic acid kind of twice over. What a crazy looking molecule. Let's write the chemical formula for this. There's 2 H's. We'll list those first, right? The H is listed first in molecules that are acids, and this has a carboxylic acid in it, so it's acidic. Let's put the H first. And then there's 1 C, and how many O's? Oh, there's 3 of them. Does that look familiar? That may be a reaction you studied. I hope it was in general chemistry. The old baking soda vinegar reaction. If you take vinegar, which has H pluses, and baking soda, sodium bicarbonate, has carbonate ions. 2 H's and carbonate form carbonic acid. That's an N, carbonic acid, which is not stable. It falls apart to produce water and the fizzing carbon dioxide. That's where the CO2 is coming from. It's formaldehyde getting oxidized twice to form carbonic acid, which then decomposes. Okay, so there's 2 reactions to this. Some of you are like saying, oh, that's cool. Okay, that makes sense. That helps me remember CO2. That's one reaction. The other reaction is, oh my gosh, why you hit me with all these reactions and all these details? I'll just remember when formaldehyde is made, it's not formaldehyde with permanganate. It's carbon dioxide. And that works too. Whatever works for you. Oh, forgot to mention, and this is one of them. There is no mechanism on exams involving potassium permanganate. And I forgot to mention it, but true for ozone. For any mechanism question on, cool. Oxidation, mild means stop at the aldehyde or ketone, mild oxidation with ozone. Strong oxidation, keep on going. After you cut it in half, take your aldehydes to the next level, carbon dioxide or carboxylic acid. Nice. Okay, there's 2 oxidation reactions for alkenes. Here's a third. This one, most textbooks just say, oh, just throw this weird reaction here. Okay, where's this coming from? Okay, this is called, for those of you who like names of reactions, right? Some of our brains are better tuned to words. They stick better. So maybe you find it easier to name the reactions and remember them that way. So mild oxidation of vicinal diols, vicinal. I've taken a little bit of Spanish. That looks like vecino, which I think means neighbor in Spanish. So this literally means a mild oxidation of neighboring diols, di meaning 2, ols meaning alcohols. So literally means 2 alcohols on adjacent carbons. So if we have, where's my notes? Do this one here. In the center of the page, so I have some room on the left side. Let's make a molecule with a pair of alcohols on neighboring carbons, right, side by side, and that's the key. They must be on adjacent carbons, side by side, not on the same carbon, not 2 carbons away. Yeah, you got the idea. So this reaction requires the alcohol groups to be on adjacent carbons. Treat it with this funky acid called, well, it looks like periodic acid, but it's periotic. Iodine is the root here. So it's an iodide. And the acid, well, lead it with an H. And then per means, I think it refers to perfect or the maximum number of oxygens. Turns out it's 4. Sometimes I'll write a water molecule under here. I don't know how I got in that habit. Water's just a solvent, it's not a reagent. But if you see some answer keys with water written under here, just ignore it. Yeah, probably that's what the solvent was, but it's not required on exams. Okay, what happens? Well, this is not an alkene. What's it doing in unit 2? It's a chopping reaction. That's why it's here. Periodic alcohols and cleave or chop the 2 carbons apart. And, well, it is not acting, it's not pretending. It is an oxidizing agent. And so where there used to be alcohols, you double up the bonds. So I had a O here, I still have an O there, but I double up the bond. That's an oxidation reaction. And we drew it before like this, which is the exact same molecule. Do the same thing over here, carbon. I'll put in the C with the O. That's what this C, there's a C here, carbon there with an O. Oxidize it, remove the H, and double up the bond. Wait, that carbon's only making 2 bonds. What else is it attached to? Oh, 2 hydrogens. Yeah, that's formaldehyde again. It's making the same reagents we saw, same products rather, through mild oxidation. Okay, do I have other notes down point? Oh, that's exactly what. This reaction and visceral dialysation of alkenes. It kind of brings me back to my first point. Why is this alcohol reaction showing up in a unit about alkenes? Well, because there's 2 ways. Alkene. Yeah, so if which we chopped with ozone and permanganate, and we treat it with osmium tetroxide and sodium sulfite, hydrogen sulfite, right? Frame delay, come on. SO3. Looking at my notes and I don't see that reaction on there, but I'm sure it works. Puts a pair of alcohols on here. Yeah, that's hydroxylation of alkenes. Yeah. And then epoxidation followed by hydrolysis. Those are the 2 ways. Oh, here it is. Yeah, my notes are wrong. You take the same molecule, same alkene, and first treat it with MCPBA to make the epoxide. There we go, there's an epoxide. And then we hydrolyze it, hydrolysis, cutting with water, with dilute acid, and that'll make the diol, the molecule with 2 alcohols. And then you can chop it with periodic acid to get something that you could have done in 1 step. With ozone. I'm thinking about the carbohydrates. So this reagent, periodic acid, is really important to carbohydrate chemists. Anyways, it's just like a miscellaneous reaction for us. HiO4 will chop diols that are vicinal, adjacent to each other, and get the same products that we saw from ozonolysis. Cool. There you go. Something to remember is that if you have a molecule with alcohols, but they're not on adjacent carbons, there is no reaction. Oh, and there's a carbohydrate reference. Yay. And there's no step-by-step curved arrow mechanism associated with this cleavage reaction. Let's do a quick little example, just kind of solidify the requirements of vicinal alcohols. Let's put another one over here. Why not? Okay, so suppose on your next exam, I ask you to predict the products. I will give you the option of writing Na for, no, I think it's NR, sorry. No reaction with an R. NR for no reaction. Is there a reaction here? Well, first of all, you have to look at the reagent, look at the starting material and say, oh, is that a reaction we studied? And you're looking for patterns, right? So you never, at least I don't think you have, seen this molecule before with 4 alcohol groups. And that's not what's being tested, it's the pattern. We have seen this reagent. This is the one that cuts right between a pair of alcohols on adjacent carbons. Ooh, that's the pattern. Is this alcohol adjacent to another alcohol? No, it's not. So this alcohol does not react. What about this alcohol? Yes, it's right next to this one. So yes, we get a karate chop right here. This alcohol is way too far away from anybody else. There's no reaction down there. The only reaction that takes place is right here at this carbon, between these two carbons rather. We get the molecules separated into two. Excuse me. Let's draw the fragments. So we got to here, right? So we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then there's an O for this alcohol, but then we oxidize it. It's not an alcohol, it's an aldehyde. Well, just make a double bond. That's all you have to do. And don't draw on this bond because it got cut. Instead, you get the second piece of the molecule with 3 carbons. 3 carbons, and then this alcohol at the right-hand side didn't react. It's too far away. No, the first oxygen in this chain of 3 is the one that helped the reaction go. It was adjacent to the L alcohol, and it's no longer an alcohol group. You oxidize that to double bond, and it turns into an aldehyde also. And that's your answer. 2 molecules here. Nice. Cool. What else we got? Well, it's the end of the oxidation reactions. Let's make cyclopropane. So there's 2 ways of doing that. Cyclopropane synthesis, to be technical. Let's make triangles, to be not so technical. Cyclopropane synthesis, use a chloroform base. I wish I was there. Around with the goggles on, totally being safe, but saying, I want to just know, take this solvent, chloroform, keep that in the fume hoods, knock you out. You don't want to be an alkene. How about cyclohexene? Cyclohexane with an ene, cyclohexene, alkene. And let's just mix it in, low chloroform as my solvent, and I don't know, what do you feel like mixing? See if we get a brand new reaction that's never been discovered. Oh, let's just go grab some sodium hydroxide. Kind of boring, but hey, it's a strong base. Where's the acid? Where H is around here? I don't know if the student or the graduate student or the professor or whoever, the lab worker, if they're even giving this much thought, they're probably just clowning around. That's what I imagine. And it's like, oh my goodness, there is a cool reaction that takes place. And it probably took some work to verify that this is the structure, but you make a triangle here. This new carbon comes from the solvent. And this carbon still has 2 of the original 3 chlorine atoms of chloroform. You get a pair of wedge bonds because the cyclopropane ring, if it attacks another ring, if you make cyclopropane from another molecule that already has a ring, then the new ring is on one side of that original ring. Both carbons either come towards us or both go away. It's the cis isomer only. We call this syn addition. Both bonds are wedge. Okay. The mechanism is not on the exam, but I'm going to show you a little bit of it because it's kind of cool. Not on exam. But what takes place here is hydroxide ion, such a strong base, it's going to find it from somewhere. And it turns out it finds it from chloroform. There is a hydrogen on chloroform. Chloroform is not normally an acid. It's not acidic, doesn't change the pH of water, but it's hydroxide ion. Maybe they had to heat this up a little bit to make the reaction go. Give this hydroxide ion a little more energy to remove that hydrogen from water. And then this bonding electron does a U-turn onto carbon. And now carbon is negatively charged. Okay, and if you know anything about electronegativity, carbon's not electronegative. It's having a hard time dealing with the negative charge. The chlorines are helping though. Chlorine is electronegative, so it's pulling on these bonding electrons, pulling away from the carbon And this carbon was like, yeah, you guys can take those electrons. I got this stupid lone pair. I don't know what to do with because I'm not electronegative. And actually, one of the chlorines just snaps off. It's like, okay, I'm out of here, and takes these bonding electrons with it. So I just picked the top chlorine. And so now this carbon is stuck with 2 chlorines, and it's missing a bond. But if you count up all the protons and you count up all the electrons, they're balanced. This is a neutral molecule. Crazy. But it's very reactive because carbon is only making 2 bonds and has a lone pair. It's like, whoa, carbon, what are you doing? You need 4 bonds. And he's like, yeah, I know. Where am I going to get another bond? Oh, look at this nice pi bond here. And this molecule called a carbene attacks a pi bond. And makes a 3-member ring, the triangle, the cyclopropane. That's cool. This anion, carbon bearing a negative charge, well, the negative charge sits on carbon. It's actually called a carbanion. Whoops. We saw carbocations before, so same deal, right? Carbanion with a B. Anyways, not on exam, but it's kind of cool. Anything else about that? No. Other than someone came along and said, that was cool. Wish I thought to mix a little base with chloroform, make cyclopropane. And then someone, you know, there's always somebody in every class that's like, yeah, but I really don't want my cyclopropane to have any halides on it. And that's what this reaction always does. The extra carbon that completes your triangle, right? 2 carbons of the triangle come from the alkene. 3rd carbon, the point of the triangle, has to come from chloroform, and that carbon always is going to arrive with 2 chlorines. So someone else said, I don't want my cyclopropane with chlorine. Can you find another way to make cyclopropane rings? So there's 2 guys, Simmons and Smith, developed a method, and it takes, we can just take the same alkene, but you can take other alkenes. And if you take diiodomethane, and that name is way too long for this small molecule, but yeah, methane with 2 iodine atoms. And in a mixture of zinc and copper, you might see the word zinc with copper. And so what's happening is that you form this little amalgam. It takes, I forget exactly how you do that, but you activate or energize the zinc. And now what it does, it forms the carbene, where carbon has 2 hydrogens, and it'll look just like this carbene, except no chlorines, only H's. Turns out that's extremely reactive, stays bonded to the zinc. It's kind of weird. It's a weird mechanism. It's so weird. We're not putting it on exams. So the mechanism on the exam. All you need to know is, hey, if you want a cyclopropane ring with no halides on it, then your best bet is CH2I2 with a little zinc and copper. Sometimes you see a little slash here between zinc and copper. And yeah, you need ZN, CU on your exams for full credit. Those are the reagents. And you get Synadish to, or whatever you want to do. Synadish. I think that wraps up the reactions of the alkenes. Yay! I know it's quite a long list. I'll post something on Canvas to kind of kind of a summary of all the reactions of the alkenes. That'll be helpful. Oh, a little note to self. Does synaddition always result in cis products? We saw that before with epoxidation and something else. The answer is no. So if you have not an alkene that's not a ring and you make a cyclopropane ring out of it, I don't know, I'll use the base. Oh, doesn't have to be sodium. Sodium hydroxide, it can be potassium hydroxide. Sodium, potassium, or hydroxide is the base. When you fill in the reagents on the exam, you can choose your reagents. I'm picking today, I want to use a little potassium. Who cares? It's hydroxide ion that matters. You do get syn addition, which means the two bonds are on the same side. And this is cis. The two methyl groups are on the same side of the ring. So if you kind of imagine this triangle being in the plane of the computer screen or your phone screen, whatever, the methyl groups are coming out towards you. And if you start with the trans and treat with the same reagents, then you also get, whoops, not an H, you get a pair of chlorines on that carbon. And now if you look at your triangle's kind of standing up here with one methyl, this one towards the left-hand side. And this other methyl's behind the ring, the cyclopropane ring. This is the trans isomer. This one is cis. Okay, so it's true, you always get syn addition, there are wedges with a new group, but the product, you have to reassess it and decide, okay, now given the structure, is this a cis or a trans product? And here, I hope you see that, no, this is not a cis product, even though it is syn addition. Yeah. Okay, those are the reactions that could be, can't put everything on the exam. There's still more reactions of alkenes that are not on the exam. Here's one that's really important. I feel a little guilty not putting it on the exam, but hey, the list is getting too long. So there's a whole class of reactions that make plastic. And you take an alkene, alkenes are really just really reactive. And there's ways of linking one alkene to another one. So if you take styrene, this molecule, which has an alkene, carbon-carbon double bond attached to one of nature's favorite functional groups, the benzene ring, the arene, or the aromatic compound. And you get a big beaker with a whole bunch of these styrene molecules, and you put in an initiator. Yeah, we're talking about free radical reactions. Do you remember the free radical halogenation of alkane reaction? Sure you do. It was the first reaction of Unit 2. That's where you take Cl2 and Br2, a little heat and light with an alkane, and a hydrogen will be swapped with a halide. And the mechanism had 3 steps: initiation, propagation, termination. Okay, don't freak out. That same mechanism, which is not on the exam, is a way of making plastics. So initiation, propagation, termination. It's pretty funky. You can actually link a whole bunch of these styrene molecules together, make one big macromolecule. The mechanism might look like this. You get your initiator in the propagation. It's an initiator, and the initiation step will make a free radical, a single dot, and then the alkene will split. Little fishhook arrows will connect the radical to one carbon. The other pi electron will then connect with another radical for another pi electron. And we just keep doing this and so on. And I don't want a double fishhook arrow, right? Double arrow means 2 electrons moving, but in free radical reactions, only 1 electron moves. And what's happening is one big molecule forms a whole bunch of styrene molecules. And that new molecule is called poly means many, polystyrene. That should be just this line here. And you don't get just one single molecule that you can pull out from the beaker. No, you get a whole bunch of these long chains, big long chains, lots of benzene rings hanging off the end. And then all these chains can stack together. What you can do is dissolve it in something and then blow air through it to make little beads of polystyrene that you can pack together and make like styrofoam cups. Cool. None of that's on the exam. So it's just kind of interesting stuff. A whole bunch of plastics can be made from alkenes. Not all plastics. There's other ways, other plastics that are made by different methods from different materials, not alkenes. But this is a good way of making a bunch of them. Kind of cool. All right, last topic is the topic of structure determination. Structure determination, yeah, determine the structure of the molecule. Essentially, you want to identify the molecule. These are like puzzles. So a lot of students find these enjoyable when they solve them. The first time through, it's a little challenging. You don't know how the game is played. You're still getting used to all the reactions. So the first thing you need to do is not start here. Go back and learn these reactions first. And then come back and try these. Okay, so back in the day, if you found a brand new molecule out in nature, you want to know what the heck is this molecule? What's its chemical structure? What does it look like? Here's some things you could do. So through other chemical means, reactions, analysis, we've discovered that here's the chemical formula. It's C10H16. Yeah, but what does it look like? Is it 10 carbons in a row, or the rings, or double bond, triple bonds, whatever? That's what we want to find out. What is its structure? They find it in nature. It's a pleasant smelling hydrocarbon. Sounds like it comes from petroleum. So dig it up out of the ground. And the chemical formula is C10H16. No, you don't dig it up out of the ground. It's been isolated from the oil of marjoram. Okay, so that's a plant. Yeah, it's a natural product. Cool. All right, so don't dig it out of the ground. Pull it out of some plant. Anyways, want to know what this is? Well, here's some things you can do to try and get some information about what is this. So first clue we had to solving this puzzle is we have the chemical formula. Next clue, take some of this molecule, don't use it up, don't use all of it, just a little bit, and do hydrogenation over a palladium catalyst. What? Hydrogenation is where you take molecular hydrogen, H2, and use a palladium catalyst. Hey, we saw that reaction. That's the reaction that takes an alkene into an alkane. It adds hydrogen. This is an addition reaction. And so then it goes on to say what exactly is happening. Alpha terpenine reacts with 2 molar equivalents of H2 to yield a hydrocarbon, C10H20. Okay, started with 16, ended with 20. If you do the reaction one time, you add 2 H's. They're saying you add 2 molar equivalents though to get 4 H's. So this happens 2 times. In the molecule of alpha terpenine, I gotta look that up, see how this should be pronounced. We're doing the hydrogenation twice. There must be a pair of alkenes. Sorry, that's an H. So somewhere in the molecule, there's 2 C double bond C bonds, and they both turn into alkanes, C single bond C. And then we get 1, 2, 3, 4 new H's. We go from 16 H's up to 20. Okay, on ozonolysis, oh wait, what are they doing here? Ozonolysis is cutting with ozone. You cut double bonds. So what's not being said here is you go back and take some more of this alpha terpenine, the one that has a carbon-carbon double, actually has 2 of them, 2 carbon-carbon double bonds, and you do ozonolysis. So you cut it with ozone, step 1, cut it with ozone, O3, followed by reduction with zinc and acetic acid. Oh, we knew the reaction is zinc and hydronium, zinc and hydronium. So in this specific case, their source of acid was vinegar, acetic acid. And what happened? You produced glyoxal and 2-methyl-2,5-heptanedione. Don't worry about the names, look at the structures. Wherever there was a double bond, you get 2 fragments capped with cotton balls, oxygen. Got any cotton balls in these molecules? Yeah. So what does that mean? That means wherever there are currently C double bond O's, there used to be a double bond. Ooh, that's a good clue. Okay, this problem is pretty kind. It's going to give you some steps, step by step, to try and get to the actual structure. First of all, how many degrees of unsaturation does terpenine actually have? Well, you do need to memorize that formula because we're going to see puzzles quite a bit. So it's going to be useful to you. So C10H16. If we want the degrees, well, first you calculate how many hydrogens are possible if it were to be saturated. That's 2n plus 2. And then you subtract the actual number of hydrogens and you add your adjustments, right? Adjustments. There you go, can't spell. And our adjustments could be halides. They act like hydrogen, add them in. They could be an oxygen. That's like the number 0, just ignore it. Or it could be a nitrogen atom, which means they do the opposite of hydrogen. So subtract a hydrogen every time you find a nitrogen in your molecule. Oh, don't forget to divide the whole thing by 2. Okay, so n is the number of carbons. So 2 times 10 plus 2 more. Minus the actual 16, no adjustments, all divided by 2. 2 times 10 is 20, plus 2 is 22. 22, yeah, and you don't need a calculator for this. I believe Proctorial does have a calculator if you want to just check your math. Show your work. So if you make a silly math mistake, I can still give you credit for the rest of the work. But yeah, you're college students, you guys can do simple multiplication and addition, subtraction. 22 minus 16 is 6, right? 6 plus 16, 6 plus 6 is 12. Yeah, that's a 2, carry 1, 22. X divided by 2 is 3. There's 3 degrees. And you get partial credit for answering part A. Part B, how many double bonds and how many rings does it have? How many double bonds and how many rings does it have? Well, from the hydrogenation data, it reacted twice with H2. We know there's 2 alkenes, there's 2 pi bonds. Now, some of you are saying it could be a triple bond. I agree, it could be. And in fact, we'll see in our next unit, unit 3, that triple bonds react with hydrogen also. So let me just tell you, they're assuming, and correctly so, that the molecule alpha terpenine actually only has alkenes, no triple bonds, no alkynes. Okay, so moving on. The hydrogenation said there's 2 double bonds, so this is part A. Part B, 2 CC double bonds from H2 palladium reaction, but there's 3 degrees. If there was a 3rd double bond, hydrogen gas would have chopped that, not chopped. Hydrogen gas would have reacted with that to make an alkane. It didn't, which means there's not an alkene in there. So the 3rd degree must be a ring. So there's 2 alkenes and there's also a ring together, that's 3 degrees. Cool, that answered part B. Part C, propose a structure. Okay, so our structure has to have 10 carbons and it'll have 16 hydrogens. It's got to have 2 alkenes in it, 2 pairs, 2 double bonds rather, and there must be a ring somewhere. But more importantly, we haven't used the ozonolysis data yet. Ozonolysis data up here in the top left says wherever you cut a double bond, you get a pair of C double bond O's. Okay, this C double bond O, these pair could not have been attached together. That would have made a, I don't know, triple bond, something weird. No. One of these C double bond O's must have attached to the others. Maybe this one, maybe that one. So what you can do, I think I have some blank space over there. Yeah, I do. What you can do is, let's copy the bigger molecule over here. So I got C3, C double bond O, CH2, CH2, and then the C double bond O. What else is there? There's a CH with a branching methyl, and another CH3. And then, where the cotton balls meet, we're going to put in our C double bond O's. These two C double bond O's are these two here. Or in other words, I'm going to flip this molecule, the glyoxal, upside down. Wait, what is that? Okay, so we're taking the C double bond O, and now flip your phone upside down, flip your laptop upside down. So that actually looks like this. And stick it right here. This molecule is the same as this one. And now you got the double bond O's facing each other, because that's where we cut it. We did the chirotic chop right here, and another chirotic chop right there with ozone. So we start with an alkene right here. So this C connects to this C originally through a double bond that got chopped. And let's just draw the rest of the molecule. So this carbon on the bottom had a methyl group. I just drew it in. There's two carbons, CH2, CH2. And then let's move this out of the way. Sorry, so I have more room to draw. And then there's the C double bond O again, but this C double bond O pairs used to be an alkene. And there's an H up here, and then these two carbons are linked together. And then what's the rest of the molecule? Let's see, this C is connected to a CH with two methyls. And if you're to leave this, I would give you full credit. That is the structure of alpha terpinene, pinene, terpentine, something. Now, if you look at the answer key, I think what we did is we kind of expanded this and drew a little more in its original shape. Let's see how many carbons. Three, four, five, six. This is a hexagon. Let's let this carbon be right here. So it's double bonded here. This carbon's the one right next door, and it's double bonded right there. So this carbon, that carbon are these two carbons. At the end of the double bond is this carbon with a CH and a pair of methyls. Squeeze it on the page. And then we have 1, 2 carbons. That's 1, 2 carbons. And then we hit the other alkene carbon. There it is. And it has a branching methyl. And there we go. There's alpha terpinene, however it's pronounced. And we solved the puzzle. That's pretty cool. All right, that's plenty for now. Thanks. See you in the next video.